Okay, this is going to be the review for the universe unit. Really, there's not a whole lot to this unit. It's basically just being able to describe components of the universe, the origin of the universe, the Big Bang, and the evidence supporting that, light years, and characteristics of stars, including HR diagrams. So, again, pretty basic unit, pretty straightforward. I'm going to get started. Components of the universe. Universe is everything we know of, basically. So, planets, moons, stars, solar system, galaxies, nebulas, and a whole lot of empty space. As I told you guys before, space is 99.999% space. So, that's why they call it that. Going from small to big, or big to small, universe would be the largest thing. Ignore the nebula. It's kind of not good. Nebulas and galaxies make up the universe. They're kind of the big things. Within galaxies, we have solar systems. Within solar systems, we have a single star or maybe a couple of stars. There's planets within solar systems that revolve around those stars, and then moons that revolve around those planets. So nebulas are just clouds of dust and gas. That's how stars are born. The only difference really between nebulas and stars is that stars produce light and heat. Galaxies, there's an example of a galaxy. I'm not sure if this is a spiral or an ellipse, but nonetheless you get an idea that it's full of millions of stars. Basically they're held together by gravity. So each galaxy having millions of stars, there are millions of galaxies, or even billions. And there are three major types of galaxies. Spiral galaxy, elliptical galaxies, which are kind of like a football shape or a circle shape, and irregular, which have no definite shape. All of them have in common that they're all made of stars. Here's an example of an artist's rendition or rendering of our Milky Way galaxy. And you can see that we are one of the dots. One of these dots represents our sun. There are millions or billions of other dots in our galaxy. So we're kind of toward the outside on one of the spiral arms. It's believed that in the center of the Milky Way galaxy there is a black hole. Again, a lot of students confuse this for being the sun and the planets revolving around it. But again, all of these dots are stars. So our sun is just one of the dots. A couple of things about our galaxy: it's spiral shape, 100,000 light years in diameter, 200 billion stars home to our sun. We're about 2/3 away from the center. And we orbit the Milky Way at about 235 kilometers per second. Here's the Andromeda Galaxy, which is another spiral galaxy. That one is 2.5 million light years away. So in other words, the nearest galaxy takes 2.5 million years for light to get to us. So that's pretty incredible in terms of the amount of distance that is. Largest galaxy in our area. So the big theories involving the origin of our universe would be the Big Bang theory, oscillating theory. Geocentric and heliocentric both describe the organization of our solar system. So the Big Bang is the universe was created from one instantaneous large explosion outward, and the idea that all the matter that was in our universe started in a single point and expanded out from that. Oscillating theory states that the universe grows outward until gravity pulls it back in. Geocentric is the idea that everything revolves around Earth. And heliocentric is that everything revolves around the sun. So, going back to geocentric, this is false. This is not the way that this works. This was believed a long time ago before Galileo came up with the heliocentric model. Going back to Big Bang theory, the idea that our universe was created from the instantaneous explosion outward. If that was true, then matter would be expanding outward from that point, and that's actually what we do see when we look at galaxies in space. We see a red shift indicating that galaxies are moving away from us, and that's sort of what kind of created this whole Big Bang Theory. So that's it for the universe. I'd like to go into a little more depth on redshift and blue shift. So this is really, really basic. If an object is moving toward the observer, then we see a shortened wavelength of light. We can see that this one is shorter than this one. So the effect of that is we see more of the color blue. If an object in space in our universe is moving away from us, then we see more of the color red, longer wavelengths of light. Another way of thinking about that is this. If the object was at rest, this would be its electromagnetic spectrum. And you can see the lines represent the kind of light we receive from that particular object. The top one shows moving toward us would be a blue shift, so all the lines literally shift from where they were toward the blue, toward the color blue. Versus if an object is moving away from us, it shifts toward the red. So the easy way to remember that would be red away and blue to you. We have longer wavelengths of light with an object moving away and shorter wavelengths of light with an object moving toward us. It's called Doppler Shift or Doppler effect. And we experience that with sound due to the change in frequency as objects move. An example of that would be like the ambulance siren that we heard previously. Going back to the next topic, stars. Our sun is one type of star. A lot of people think that our sun is not a star. Stars create their own light, and they do that by nuclear fusion, which is a chemical reaction. So we've got atoms slamming into each other and create larger atoms. Like, for example, two hydrogen atoms come together and they create a helium atom. The force of that and the effect of that is it releases energy. Stars are based on classifications based on four things: size, brightness, temperature, and this says luminosity, but really it should say color. So again, our sun is a speck in the Milky Way. There are lots of different types of stars. There are lots of colors of stars. The way that we classify stars is with a diagram called the Hertzsprung-Russell, or HR diagram. So you can see on this diagram we have quite a bit of information, really. We've got on the x-axis surface temperature. And you can see it goes from high temperatures, 50,000 degrees Celsius, to low temperatures, 3,000 degrees Celsius. Related to that would be color. We've got our hottest stars, the blue ones, and it gets cooler with white, and then yellow, and then red, orange, and then our coolest type of star, which is kind of opposite of what you would expect would be red. On the y-axis of an HR diagram, we have our brightness, also referred to as absolute magnitude or luminosity. And as you go up on the scale, it gets increasing brightness, brighter stars. So we have our hottest stars over here on the left, our blue ones. We've got our coldest stars on the right with our reds. We've got our brightest stars at the top of the diagram. And we've got our dimmest stars near the bottom of the diagram. If you notice main sequence, as you go hotter on the main sequence, it trends upward in brightness. So hotter stars will be brighter. Larger stars, like the supergiants, are brighter than the giants, which are brighter than the equivalent main sequence, which are brighter than the white dwarf. So size and temperature do play into effect with absolute magnitude. This is just an overview of the life cycle of a star. The main thing you need to know is our low mass star turns into a main sequence, that would be our sun, which eventually will turn into a red giant and then a white dwarf. That's kind of the life cycle of a star like our sun. Other stars, if they're larger than our sun, high mass stars, they could become red supergiants and then eventually possibly explode into a supernova and either become a neutron star or a black hole. Talking about nebulas being the area where stars are born, main sequence, red giants, white dwarfs, black dwarfs is just a dead star, blah blah blah. This is repeated for some reason. Oh, this is for a massive star, so red supergiant, supernova, and a neutron star. You don't need to know a whole ton about that. Very massive stars could eventually become a black hole, which is something that's so small and dense that even light cannot escape its gravitational pull. So the escape velocity of any object exceeds that of the speed of light. Theoretically, that's what's in the center of our Milky Way galaxy, and that's what pulls everything in toward it. Blah, blah, blah. Difference between apparent magnitude and absolute magnitude. HR diagrams, if you go back to that, HR diagrams, there we go. We're measuring absolute magnitude. So in other words, our sun is right here. It's not that bright. It's average. If you go high up to like Rigel, that would be an extremely bright star. So that's called absolute magnitude. We don't measure relative magnitude with HR diagrams. So relative magnitude is which one is the brightest from Earth, or also known as apparent magnitude. So from Earth, obviously our sun appears to be the brightest star in the sky. That's because it's really close. It also feels like it's the hottest star. So that's just kind of the difference between apparent magnitude versus absolute magnitude. Our sun, again, appears to be the brightest and feels like the hottest, apparent magnitude, but absolute magnitude-wise, it's pretty average. And this goes on to talking about electromagnetic spectrum, different kinds of light. Longer wavelengths of light would be like radio waves, microwaves, infrared. Shorter wavelengths of light would be gamma rays, X-rays, and ultraviolet. So you can see here kind of the effect as the waves get shorter and shorter. The frequency also gets higher and higher, which means there's more energy. Radio waves are like the length of a football field. If you're looking specifically at colors, the longest wavelength of color would be red, which is why we see red shift when light is kind of stretched as objects move away. And over on the other side, we see the short wavelength blue and purple colors, violet, which indicates shorter wavelength than object possibly moving toward you. Parts of a wavelength is just from crest to crest or trough to trough. Amplitude is the height of the wave. Crest would be the top of the wave. Trough is the bottom of the wave. Pretty straightforward there. Doppler shift, we talked about that already. Red shift means it's moving away from Earth. Blue shift, moving toward Earth. So here we have an object that's moving away from, toward Earth. And this one would be moving away from Earth. This one would be at rest. Same idea. We've got an object at rest. An object moving away from us shifts toward red. An object moving toward us shifts toward blue. You can also use the spectrum to identify elements within the universe. So as we look at objects in space, we get these spectral images and we can match them with different elements to figure out what is contained in objects in space. The only other thing that you really need to be aware of is the concept of a light year. So a light year is equal to 9.46 times 10 to the 15th meters, which is a fancy way of saying 9.5 trillion kilometers. That's a very, very large distance. So what a light year is basically the distance that light travels in 1 year. So to give you an idea, light travels at the speed of 299,792 kilometers every second. So from Earth to Moon would be 1.29 light seconds. Earth to the Sun would be about 8 light minutes. Earth to Mars is about 12.7 light minutes. Earth to Proxima Centauri, which is the nearest star outside of our solar system, would be 4.3 light years. So to recap, we don't measure anything in our solar system with light years because it's too small. Our solar system is measured in light minutes, not light years. So a light minute would be obviously much less than a light year. Rather than use light minutes, we usually measure things in our solar system in kilometers or astronomical units. So what do we measure with light years? We use light years to measure distances between our area and other stars, or distances within our galaxy, or even distances between other galaxies in our universe. Very, very large, very massive distances. So what is a light year then? A light year is how far light travels in 1 year. So for example, if you're looking from Earth to the other side of the Milky Way galaxy, that'd be about 52,000 light years. So to put that in perspective, it takes light 52,000 years to travel from the edge of our galaxy to Earth. It takes light 4.3 years to go from Alpha Centauri, or excuse me, Proxima Centauri, our closest star, to Earth. So really, when we look at Proxima Centauri, we're looking at an image that is 4.3 years old. That should pretty much sum it up. If you have any questions, please try to write them down and ask me before the test tomorrow. I hope the review was helpful. I'm sorry it ran a little bit longer than I originally wanted it to, but I hope that the information that it gave you helps you on your test. Thanks. Have a good day.